So now we'll go on with reactions of amines in these next two lectures. So here you can see the preparation of amines. This will just be a review, a couple of methods of review. Then preparations via substitution reactions, preparations via reductive amination, synthesis strategies, and acylation of amines. Then the next lecture, we'll have additional reactions of amines. So, preparations of amines. The reaction that you saw in Chapter 7, Klein's Chapter 7, bromine can be replaced by cyanide, or by cyano rather, by a simple SN2 reaction. You will remember that this anion simply comes in, does a backside attack, displaces bromide, and so now you have the nitrogen atom, which will become the nitrogen of the amine. So you have augmented the carbon skeleton by one. This is one of the important reactions. You don't have many of these reactions that increase the carbon skeleton. And so you simply have to reduce this carbon-nitrogen triple bond. You will remember that one way to do that was through lithium aluminum hydride. And so this is your first synthesis. This is a review of material that you had in Chapter 7. Another review is from your carboxylic acid using thionyl chloride. You create the carboxylic chloride, and so and that can be then reacted readily with ammonia to replace the carbon-chlorine bond with the carbon-nitrogen bond. Then once again, you simply reduce the carbon-oxygen double bond using LAH, so you have converted C double bond O to CH2. So now the carbon skeleton is unchanged here. So this is another review of a reaction that you've already seen. Still another review, preparing aniline from benzene. So you can use nitric acid with sulfuric acid, and you do the electrophilic aromatic substitution, replacing the CH bond with the carbon NO2, and then reduce the nitro group using catalytic hydrogenation or one of these metals with acid, and then following it with sodium hydroxide. So this is another way to synthesize an amine, which is a review. If you have ammonia, you can easily synthesize a primary amine. Here, this shows how to get the alkyl group onto nitrogen. So remember that the nitrogen lone pair is very basic, and so this will simply do an attack at carbon, SN2, an SN2 displacement of iodide, and then another molecule of ammonia or some other acid can pluck off this proton, and you have converted ammonia to methylamine. Now, the problem in trying to use this to synthesize a primary amine is that the alkyl group attached to nitrogen here, the carbon will have electron density withdrawn by nitrogen, and that will make this lone pair even richer in electron density, because nitrogen is highly electronegative. So nitrogen will be richer in electron density. The nitrogen, therefore, will bear a pair of electrons that is even less tightly held. It will be a larger electron cloud, and it will be more readily available for reaction, just like this one. So instead of stopping here, this lone pair will go on to attack another molecule of methyl iodide, and so you'll get multiple alkylations. And so this will not be a good way to synthesize primary or even secondary amines. You will get product mixtures. However, it is a good way to make quaternary ammonium salts by simply using an excess of methyl iodide. So that is demonstrated here. So if you have an excess of methyl iodide, you'll have the first alkylation shown on the previous slide, and then as I discussed, the pair of electrons comes in and attacks carbon to get a second alkylation. Then nitrogen will, from one of the amines present in the reaction, will pluck off the proton, and so now you have nitrogen, which is still electron withdrawing, as always, and so now it's bearing two methyl groups, and so both of these will donate electron density onto nitrogen, and so this nitrogen will be even more electron rich than that one, and so this pair of electrons will be even more basic than that one, and so it will do an attack on carbon. This is an SN2 displacement of iodide. And so now you have a tertiary amine. And so this nitrogen will be even more electron rich than the others that preceded it. So here, finally, this nitrogen will do an SN2 attack, displacing iodide, and you have the quaternary ammonium salt. Now, I might mention that you do have to use, one does have to use an excess of methyl iodide in order to achieve this, because there is another force going on simultaneously here, and that is while nitrogen is increasing the electron density as you get methylation, and the lone pair is becoming more basic as one increases the number of methyls going, so you're going from primary to secondary to tertiary amine. There is another factor going on, not just the basicity of the lone pair, but their steric hindrance, which is increasing, which works in an opposite direction of the electronegativity. So the electronegativity on nitrogen, and the basicity of the lone pair is increasing and has a tendency to increase the methylation and work towards the quaternary ammonium salt. The steric hindrance works against putting 4 methyls around nitrogen. So you have two forces, the increasing basicity of the lone pair and the increasing steric hindrance, and these are working in opposite directions. So therefore, one must use an excess of methyl iodide, and which is easily done. Another preparation of amines is by using azide. Here you have the sodium azide, conversion of the alkyl halide to an azide via an SN2 reaction. So here this is an an anion, it will do a backside attack. This is SN2 reaction, replacing the carbon-halogen bond with the carbon-nitrogen bond. And then you simply use catalytic hydrogenation or reduction to give the amine. And so this is far superior to using methyl iodide if you're trying to make a primary amine. In using this, you'll get a much higher yield of the primary amine. Here's the mechanism. There's the azide backside attack on the alkyl halide. And so then using lithium aluminum hydride, you have H- do an attack on nitrogen. Pair of electrons moves over, satisfying the positive charge. Now you have the the first of the nitrogen-hydrogen bonds formed here. A pair of electrons moves back in, forming a nitrogen triple bond. This pair of electrons moves in onto nitrogen. You lose N2 from that end of the molecule, and so here we've lost this. You can see it's expelled as a gas, and so now you have nitrogen bearing a negative charge and two non-bonding pairs, and so now you simply deprotonate water and you have formed the primary amine. Now there's another synthesis, the Gabriel synthesis. This can be used for primary or secondary amines from phthalimide, and the phthalimide is converted to an anion using potassium hydroxide, and so this is this anion is stable because it's in conjugation with the two carbonyls, this potassium phthalimide. Now the potassium phthalimide does an SN2 reaction on an alkyl halide, displacing the halide, and you have formed the nitrogen-carbon bond in this SN2 reaction. Now you can see that this does not immediately go on to form a secondary amine because the other two positions on nitrogen are blocked with nitrogen-carbon bonds. Then the last step uses aqueous acid or hydrazine to liberate the amine, and so you're going to have the dicarboxylic acid or this bicyclic compound, and the primary amine has been generated. Another method is reductive amination. The ketone or aldehyde is converted to an imine, carbon-nitrogen double bond here, and then it is reduced, catalytic hydrogenation. Sometimes a reducing agent can just be present here as the amination is done. If it is a reducing agent that does not react with the carbonyl, but does react with the imine, then what happens is, if the reducing agent is also present, as soon as the amine is generated, it's reduced. Okay, now that would not be this, but there are others that can be used, and so it can be done in one pot, a one-pot reaction. So this is one of those reducing agents, sodium cyanoborohydride. It's similar to sodium borohydride. So here is sodium borohydride, sodium cyanoborohydride. You'll remember that this is similar to the lithium aluminum hydride. This molecule, however, does not react with ketones or aldehydes. So it can be put in right here, and it will be a spectator in the reaction of the nitrogen with the carbonyl, the ammonia with the carbonyl. It will just be a spectator in that reaction. And once the amine is formed, then the sodium borohydride, sodium cyanoborohydride, will react. So here are examples. You have the carbonyl reacting with ammonia to give you a primary amine. This is after the reduction, of course. And here you can use a primary amine or a secondary amine with the sodium cyanoborohydride in situ to generate a primary amine, secondary amine, or a tertiary amine in this reductive amination. So there are 3 options to producing the primary amine, 3 new ones that you've seen in this chapter. And to review, this is the Gabriel synthesis, or the sodium azide, or the reductive amination, which we just saw. So the strategies for these syntheses, you can synthesize the primary amine from any one of these 3, and then use the reductive amination to generate the secondary amine, the tertiary amine, and then you can use the alkylation to get the quaternary ammonium ion. So these 2 will generate the primary amine, the reductive amination. You can get any of these by using the reductive amination. The acylation of amines, remember that amines are converted to amides with an acyl chloride. This is just spontaneous because the acyl chlorides are so reactive. So this is the carboxylic acid chloride, and they're very reactive. And so the nitrogen does the attack, and then the the chloride is lost spontaneously, and the nitrogen-carbon bond remains. Now, remember, you're generating HCl, and so you'll need a second mole of the amine in order to pick up the proton that's generated and left there with the hydrogen chloride. So 2 moles of this are required. The first one is required to generate the product, the amide, and the second one is required just to pick up the proton and keep this from reacting further with something else. Now here, I've got a red X across this because this reaction is not successful for monobromination. If you simply use aniline and try to do a monobromination, it is not possible. The amino group activates the ring so much that you will get the tribromo product. So this generally, it's not very useful because usually only monobromination is the goal. And so, if one wants to just get monobromination, what happens is this group needs to be converted first to a less activating group. So this group is less activating than this. So here, the problem is the pair of electrons is donated into the ring. Here, this pair of electrons is involved with the carbonyl. Okay, so you have a pi system up here. So this pair of electrons is not so available to the ring. It's involved up here, and you can actually draw the resonance structure of this. So this group is not so activating, but it is still activating, and it's paradirecting. And so it's activating, you do get the monobromination, and then once that happens, you have to remove the carbonyl using either basic or acidic conditions. So this is the way to achieve monobromination. Now another one, aromatic amines also can't undergo the Friedel-Crafts reaction directly. The amine complexes with the aluminum trichloride, and so here you have turned an activating group into a group that is deactivating. And so this, while this might be activating, what happens is when you put the reagents in for Friedel-Crafts reactions, instead of reacting to chlorinate the ring, what happens is the nitrogen associates with the aluminum, and so this ties up the reagent, and furthermore it deactivates the ring because here nitrogen is bearing a positive charge. So this is just unreactive. So this does not work. So I put a big red X through it to make it quite clear that it does not work. To achieve the alkylation, once again, the this group needs to be changed into a group that will not complex with aluminum trichloride. So once again, it is changed. You have to react it first with the acyl chloride. And so now the nitrogen, instead of being available to just complex with aluminum, the nitrogen is tied up in resonance with the carbonyl, just like before. This is the protecting group, just like before. And so now you can do the Friedel-Crafts reaction. And so this, just as before, it's orthopara-directing. So the methyl goes in the para position, and then after the Friedel-Crafts reaction, acylation, and then you remove the group using either acidic or basic conditions. So that takes care of our synthetic strategies and the first few reactions of amines. And so in the next lecture, we will look at more reactions of amines.